It's being recorded and then some kind of flat. All right, so first of all, let's recall the double integral for volume. Okay. Suppose this is a surface z equals f of xy, and on the xy plane, you have a region R that corresponds to the surface V. Okay. So this is the region R, right? And we know the volume of solid that is simply under the surface, which would be computed by double integral function f of xy over region R dA, right? Which is basically the limit of the Riemann sum, okay, Riemann sum, which is the function value for height, and then the differential of area, okay, delta area. These are old materials that we know before, right, with double integral. The region of integration is what we are looking at in this section, okay? Focused on the section as non-rectangular region. So if this is the region R here, okay, this is region R, when it comes to the XY plane, you can write the region R in this format, right? This is the region R. You guys okay?
Yes.
Okay. So as we can see that in this graph here, this region R is not a rectangular region, right? It's not rectangular, and we need to think about a way for us to express such non-rectangular region. Once again, it depends on the shape of the region R. Okay. So in the end of the last section, we looked at the double integral. Okay. I'd like to recall the double integral. The double integral is simply defined as y is between 1 and x is between 1 and 2. Okay. So x is between 1 and 2, y is between 1 and x. So we figured out if you try to sketch the region, it looks like this. Okay, this is the region R, which in this graph is triangular shape, not triangular shape. Triangular shape, we'll talk about that just a minute. Triangular shape could be expressed both in both of the x symbol or y symbol. But again, the triangular shape would give us one idea of how we can, like here, how we can express a non-rectangular region by using some description about x and some description about y. So we're going to use just this example as an introduction for non-rectangular region. Okay, so we'd like to start with y symbol region. Okay, y symbol region. Some books also call it as vertical simple because y is in the vertical direction, right? So vertical simple region. So if you take a look at this graph below, okay, this graph below, the shaded region R, okay, this is the shaded region R. It's simply bounded by two constants in the left and in the right. So if we describe it, we can describe this as x is between two constants, right? Two constants, and y is between the function in the bottom and the function on the top. So we can say x is between a and b, and y is between g1 of x and g2 of x. Is that good?
Yes.
Okay. Now, what's more importantly is if we want to describe this region, you can, not only describe, if you want to decompose this region, you can decompose it by slicing it on the x direction, right, from the x direction. So once you slice it, you would getting a bunch of vertical strips, right, bunch of small vertical strips. That's why some books also call it as vertically simple region. Okay. I typically, once we see this, I typically use an arrow sign to show this is y region, a y simple region by doing this. Let me change to another color to show what I typically do. Okay. So typically I would say in these kind of regions, let me just re-sketch it here. Function x has been bounded by two constants, so a and b, while function y, okay, Function y would be bounded by two functions, right? Two functions. Therefore, we call this as y simple region. Is that it? So in
Yes.
general, y simple region is bounded by two constants for the x, and y would be bounded by two functions. Okay. All right, so the next slide explains why some people call it vertical simple. Okay. In general, you can just think about it. We can draw a bunch of long, narrow, vertically strips, okay, vertical strips to decompose this region R. The next figure give us some more examples of y simple graph, okay, y simple region. And you can all see that all these graphs, the x is bounded by two constants, a and b, while I can draw an arrow from the bottom curve to the top curve, showing y would be bounded by these two functions. So y would be bounded by two functions, therefore this is a y simple region. Okay. All right, next is called x simple region. So x simple region basically says x is bounded by two functions of y, right? And y would just be bounded by two constants. So that can be verified once again by looking at the graph. So you can see that over here, for x simple, y would be bounded by two constants. So here's the one constant d, which is the upper bound, and here's a constant c, which is lower bound. And in my x, if I draw an arrow, okay, my x would be bounded by two functions. One is this function as a lower bound, that is h1 of y, where h1 is y. Second will be a higher bound of x, which is the upper bound, which is this graph, which will be h2 of y. So we see y between c and d, x between h1 and h2. So these type of regions, if you draw an arrow, the arrow would go horizontally. You can also say this is horizontally simple. Or if you think about decomposing this region, if you try to decompose this region, you will get a bunch of horizontal narrow strips. So it's also called a horizontally simple region. Make sense? Folks? Okay. Hi, you guys. Is everything okay? Good so far?
Yeah, everything's good.
Okay, great. So this is the x simple region. The next slide once again explains what is called a horizontally simple region, because of the horizontal narrow strips you can slice this region into. All right. This is a graph for more x simple region. Okay. X simple region, again, y is bounded by two constants, so two horizontal strips, and my x will be bounded by two functions. So you can always draw an arrow in the horizontal direction, okay, representing the x function. Okay. So it goes back to this graph over here. This triangular shaped region R, is that x simple or y simple, guys? Can we treat this triangular shaped R as y simple?
Yeah.
Yep. Say over here, let me resketch this region R. Okay. I can say it is, for the x, it is bounded by two constants, right? So as we have seen here, x is between 1 and 2. And then I can sketch an arrow sign representing y. Y would be between the lower function here, which is horizontal constant 1, and the top one will be x. So if you do this way, it's going to be y simple region, right? However,
Yeah.
due to its shape, the shape is pretty symmetric. So if I redraw the shape here, R, can I also treat it as x simple? If that's the case, how do we express this in x simple way?
Would you just use the 1, 2 value?
All right, so if I do x simple, let me change to another color so we can see it easier. If I want to do x simple, I can also say, well, I can draw a horizontal sign for x, right?
Yeah.
And then the y would have an upper bound and a lower bound. Okay, let's first of all express the y value. What is the lower bound for y here? Take a look at the graph. What's the lower bound for
1.
y? Yep, so y would be between 1. Upper bound will be
2.
2, good. All right, and then what is the lower bound for x?
Would it be 0?
Oh, okay, so that's about the first function. It intersects this region R. So this is the first function it intersects, right?
Oh, okay.
Yeah, so this is
Oh,
the
it'd be
first
1.
function. Be careful here. This is actually, what is the graph of this function? What's the function of this graph? It's y equals x, right?
Yes.
Is that y equals x? Which means another way we say x equals y, right?
Mm-hmm.
So the first function intersect is x equals y. So y would be its lower bound. Make sense?
Yeah, now it does. Yeah.
Okay. Now the upper bound would be the second function it intersects. Second function would be this, right? It intersects. What's the equation of this function? It's a vertical line, right? It's a vertical line, meaning x has to be a constant. So what is that constant here? X equals to
2.
2. Yeah, so this one here is x equals to 2. So x will be bounded between y and 2. If you express this in x, simple region. Okay?
Mm-hmm.
So this region R could be expressed in 2 different ways. You can go y simple if you draw an arrow going from bottom to top. The first function it intersects will be 1. Second function it intersects will be x. Or you can go x simple, drawing an arrow from left to right. The first function it intersects will be x equals y, so that's the lower bound. The second function it intersects is this vertical line segment, which is x equals to 2. So that's going to be the lower and upper bound for the x simple region. So triangular region could be both x simple or y simple, okay? Because you can draw arrows either from bottom to top or left to right. All right, now next, let's look at example 2. Example 2, let's take a look at this graph carefully. Okay, so we see this is the surface. Z equals to 2x squared y, right? Z equals 2x squared y. And somehow it has been simply projected to the bottom. Okay, projected to the bottom, and you got over the region R. So do you guys see this region R here? The region
Yes.
R is on the XY plane. Okay, so this is the region R, right? This is the region of integration. Okay, the integration. So my question is, for this region of integration, is that X simple region or Y simple region?
Y simple.
Y simple? Yep. Let's sketch it real quick over here. Okay. So we can see that this region has something in the bottom and something in the top, right? It's between y equals 3x squared and y equals 16 minus x squared. So if you sketch it, you first of all would have one parabola for y equals 3x squared, which goes up. Y equals 3x squared. Secondly, you should have another parabola that's y equals 16 minus x squared. Due to the negative coefficient of x squared, it should be going down, right? Facing down. And the y-intercept should be 16. So somewhere here, you have 16 up there. So we should have a graph going like this. Excuse my drawing. This will be y equals 16 minus x squared, right?
Yes.
So far, good, guys? Okay. And you can see the region at the intersection will be this region R, right?
Mm-hmm.
So obviously, for this graph, you can tell the left and the right has a constant bound, right?
Yes.
I can say there's a left bound and right bound for two constants. And at the same time, I would be able to draw an arrow that intersects this region from bottom to top for the y, right? This will be the first function that intersects. This will be the second function that intersects. So this would be a y simple region. Okay? Make sense?
Yes.
All right, next slide. We actually have this graph, and we can tell that this basically refers to what we just discussed. We can figure out this left bound and right bound. By the way, is it easy for us to figure out these two values?
Yes.
Okay, how do we find those two?
Just set the two functions equal to each other.
Yeah, for these -2 and 2, they are the intersection of these two curves, right? So you're going to let 16 minus x squared equals 3x squared, and it's easy to see that if I move the x squared to the other side, I have 16 equals 4x squared. Divide by 4 both sides, I have 4 equals x squared. Therefore, x will be plus minus root of 4, which is plus minus 2. That corresponds to this -2 and positive, right? And again, you can draw a vertical arrow to intersect those two graphs. So let's see, how do we express this region R in Y simple way? Let's first talk about the x values. How do we say about the x values? So we should just grab the x. The x will be bounded by two constants. The x will be between -2 and a positive 2, right?
Mm-hmm.
Okay, what about y? What do we say about y? Y again is in this direction for y, right? This direction for y. So you should look at the two curves it intersects. The first curve it intersects will be this curve, which is this parabola. That is y equals 3x squared. So that's the lower bound. Is that good?
Yes.
Second curve it intersects will be this parabola, which is 16 minus x squared, right?
Mm-hmm.
So this is a y simple region, as we just mentioned before. that's how you express this region R by using both x and y. Okay. So x between -2 and 2, y between 3x squared and 16 minus x squared. Okay?
Yeah.
All right, next let's look at this graph. Okay, this graph is region R. Would this be x simple or y simple? Or neither?
Neither, I was thinking.
Yeah, it's kind of like a neither, okay? Because there are so many different functions to the bottom, right? And it looks like the top may be described by using one simple function, okay? Well, unless this bottom curve, it belongs to one single function, then it could be a y symbol. Let's see. So what we can do a lot of times for these like irregular shaped graphs, there's going to be neither. But what we can do is we can try to decompose. We can decompose those kind irregular shapes in neither x symbol or y symbol into either x or y. Let's see. In this case, you can do a simple decomposition. Say I can do a simple decomposition here. Okay, I notice that this part has a very simple curve in the bottom, and this is another simple curve on top, right? So in this case, I can say that's region R1. Let me use another color. The green looks like too light over here. So I can do right here. So this will be my region R1. Similarly, I noticed that this part may belong to one simple function. So I can keep decomposing. And this, I can say this one will be my region R2. And again, I can draw an arrow to show this is y symbol. Make sense? Okay.
Yes.
Similarly, suppose the last part, let's assume this piece belongs to one single function. Then again, for the last part, I can say it's another y simple region. Okay. The bottom function will be this, and then the top function will be this. And x will be between this bound and that bound. So this will be a region R3. So this big region R could be decomposed into R1, R2, and R3. So I would say region R would be R1, union R2, union R3, and all of those are Y simple regions. Okay. So later on, if you see those neither X simple and Y simple regions, you can think of a way to transform into some X simple, some Y simple regions for integration. Okay. All right, over next, we'd like to talk about double integrals. We already know what's non-rectangular regions. Next, let's talk about the double integrals over those non-rectangular regions. Okay, first of all, we have a general principle for you to do double integral. Okay. So let region R be a region bounded below and above by the graph of the continuous function y equals g of x and y equals h of x. Then this will be y simple because y is bounded by two functions, and by the lines x equals a and x equals b. If function f is continuous on this region R, then we can perform double integral of f of xy dA over region R. Now, because this time it is non-rectangular, you gotta pay attention the way we put dy dx or dx dy. Okay. This time we've got order matters for integration. Even though the order matters, there is a general principle for you to put on the outer layer. So the easy principle you can follow would be the outer layer has to be constant. So the outer has to be constant. So constants must go to the outer layer. For example, x is bounded by two constants, a and b. Therefore, I'm going to have dx to the right and dy to the left. Make sense?
Yes.
Okay. Similarly, if region R is a region bounded on the left and the right by the graphs of continuous function x equals gy and x equals xy, so this is going to be x simple region, respectively, and the lines y equals c and y equals d. If f function is continuous on R, then the double integral of function f of x, y, dA over R, this time y is bounded by two constants, so we should have the constants in the outer layer. So c and d match in the dy, and dx would be inside. Okay. Again, order matters, but it's not hard for you to determine how do you put the order. Okay. The general principle will just be constants must be in the outer layer. Okay, with this in mind, let's recall the question that we did before. Is that from the previous graph? Integration of 2x squared y dA over region S, where S is the region between y equals 16 minus x squared and y equals 3x squared. Okay, let me see if I have attached a graph. Yeah, so this is the graph that we have seen before, right? The region R is bounded by two curves, 3x squared and 16 minus x squared. And the surface on top is 2x squared y. Okay. So let's go ahead and evaluate this double integral. So first of all, we need to make sure how do we write this dA into dx dy or dy dx. Okay. So I'm going to bring up the graph that we used before, okay, which is to show this region as. So 3x squared and 16 minus x squared. This is the region S or region R. Over here it's called region S. So again, region S. And we have seen that the left bound and right bound we've calculated as -2 and 2, and we can sketch a vertical arrow to show the y. Right? The region S could be written as -2 less than or equal to x less than or equal to 2. And y would be between. Guys, how do we express y? Y would be between
The two equations.
yeah, the two curves. Which one
Yes.
comes first?
The lower bound.
Yeah, the lower bound, which is the
3x squared.
Right. Okay, so 3x squared and 16 minus x will be the upper bound. Okay. All right, so let's see. With this in mind, let's go ahead and write down this double integral. So double integral 2x squared y dA over region S to be further written as, let's retain the integrand 2x squared y. And let's go ahead and follow the direction. And as we said, constants must be in the outer layer. So x1 must be in the outer layer. So we should have -2 to 2 matching dx. And 3x squared, 16 minus x squared matching the inner layer. Is that good?
Yes.
Okay, that's how you set up. So over here, in this case, my dA, differential of the area, dA has to be dy dx. Okay? All right, next, let's go ahead and evaluate this double integral. So we're going to use the method where we discussed it last time. We're going to start with the inside and go to the outside. Okay. So let's, first of all, let's start with the inside. Okay. So we're going to do integration of 3x squared, 16 minus x squared, 2x squared y dy. Is that good?
Yep.
So antiderivative over here, y is the variable, right? So antiderivative will be 2x squared times
Y squared
antiderivative of y. Y squared
divided
over
by
2.
2.
Yep. And over here, don't forget that y is between 3x squared and 16 minus x squared. All right, I'm going to continue here. So 2 and 2 could be reduced. We have x squared, y squared. Y equals 3x squared as the lower bound, 16 minus x squared as the upper bound. Therefore, let's go ahead and plug 16 minus x squared for y and plug 3x squared for y and subtract those two. So we have 16 minus x squared minus whichever you get when you plug 3x squared in. So x squared times 3x squared, that's y, and then squared. Oopsie, go back, there, right. Is that good?
Yes.
Okay, so basically you can take out the x squared, right, as the common factor, and you only have 16 minus x squared minus 3x squared, which I could just read the square. You're getting 9x to the 4th. Okay, let's see. I'm going to go ahead and expand the 16 minus x squared minus 9x to the 4th. This shouldn't be hard because this is a perfect square, right? Perfect square. So we should have 16 squared, which is 256. And subtract 2 times 16 times 30. So x squared is 32x squared. And I'm going to have add x to the 4th, right? Because you're going to have x squared, which is x to the 4th, minus 9x to the 4th. So that's minus 8x to the 4th in total, which would give you 256x squared, if I distribute the x squared, minus 32x to the 4th, minus 8x to the 6th. Is everything good?
Yes.
Okay, this is for the inner integration, right? Inner integration. And then we just have one more step to do. Okay, let's see. And we have outer integration, which is negative 2 to 2 dx. And let's just copy this piece over here. So 256x squared minus 32x to the 4th, and then minus 8x to the 6th dx. All right, so we would be getting 256 x cubed over 3 minus 32 x to the 5th over 5 minus 8x to the 7th over 7, and then evaluate at those two ends, negative 2 to 2. Right?
Yes.
Okay, so I'm not going to finish this calculation, but you know what to do next, right? You're going to plug 2 ends and put negative 2 ends and subtract those two amounts, right?
Yes.
That's going to be your and that's going to be your answer. Okay. So by doing this problem, you guys probably have seen that we're pretty much doing the same thing as we did last time. The only thing different this time would be how do we set up this dA? How do we do dy dx or dx dy? We can just randomly say, let me just do dy dx or dx dy. No, it should be based on your description of the region of integration. Okay, we always put the constant in the outlier, in the outer layer and put the bounded function in the inner layer. Okay. In this question, what we have computed is basically the volume of the solid under the surface. Okay, so this answer here basically talks about volume of the solid under surface, z equals 2x squared y over the region R. Okay, the region R or S. Do we call it region S? Yes, so which is going to be this part of the solid, right, under that surface. So back to that?
Hey, Dr. Wu.
Yes, yes, Romero.
I thought we were calculating like the area of region R, since we weren't using the function z.
We are actually using
volume.
the function z. See here? This is your z.
Oh, never mind. I
Right?
forgot that part.
Yes.
Okay, never mind.
Well, I intentionally put a z here, so that is a z. Okay, just to match the graph that we used it before. So this is a z, 2x squared y, and we're integrating over the region R. Sorry, I call
okay,
it
that
R
makes sense.
yeah,
okay,
right. So,
I got it.
So the amount you get is actually the volume of the solid under the surface over the region R. Okay. All right, I'm going to let you guys try the next question. Okay, so apparently at this time you have a surface f of x, y, which is 2 plus 1 over y. Okay, it's going to be this surface. And it's over this region R. Again, this region R, you can tell that it is a triangular region, right? Looks like that. So it is bounded by y equals 1, x equals y, and x equals 8 minus y. You probably want to re-sketch the region R in XY view. So I think, yeah, let me go ahead and do it. So we have x-axis and y-axis. First curve we see here is x equals y. We know this is the same as y equals x. So y equals x. It's going to be this one here. Second curve we see is y equals 1. So that is a horizontal line at y equals 1. Okay, here. Y equals 1. Right?
Mm-hmm.
And lastly, we have another one, which is x equals 8 minus y. Okay, if you want to sketch it, you probably want to doing another way. You can we are more familiar with y equals something, right? So let's write this as y equals 8 minus x. Is that good? Y equals 8 minus x. 8 minus x is going to be a straight line, right? Which has y-intercept at 8. Okay. And the slope will be -1. So it should go like this. This is y equals 8 minus x. So these three lines intersect and you would get a region R. Here is a region R. Good?
Yes.
All right, let's see. If I shade this region R, how would you like to sketch your arrow? Would you go your arrow from bottom to top or draw your arrow from left to right?
Left to right.
Left to right would be simpler, right? Yes, left to right. Let me go switch back to my red. All right, so let's go left to right for my X, right?
Mm-hmm.
So this R would be X simple. Okay, for X simple, we should express Y between two constants and X between two functions, right?
Yep.
I think here it's easy for us to express the X because you already have all the functions outlined. So X, first of all, is intersects this straight line, which is x equals y. So lower bound will be y for x. Good.
Mm-hmm.
Secondly, x intersects this straight line, right? We know that's y equals 8 minus x, which is the same as what it tells you originally, x equals 8 minus y. The upper bound will be 8 minus y. Okay, so we have figured out the two boundaries for x. What's the boundary for y here? Remember, this is your region R. So
The first one would be 1.
Yeah, so the first boundary will just y be 1. Second boundary is where this region R ends for y. So you can tell from the graph it should be here, right?
Mm-hmm.
Okay, what is that value? How do we find that value?
Where the two
It's
the two intersect.
Yep, it's the intersection of those two lines, right? Two lines. Okay, so let's see. One line is y equals 8 minus x. So you say 8 minus x. The other line would be this straight line, which is x, right?
Mm-hmm.
So we have 8 minus x equals x, getting x would be 4, right?
Yep.
But that's not what we're looking for. We're looking for y. Don't forget about it. We're looking for y. So what is the y in that case?
4.
What's the value? Yep, because y equals x. So y again would be 4 as well. So here would be 4, right?
Mm-hmm.
So the upper bound of y would be 4. There we go. We have figured out the expression of this x simple region. Y would be bounded by two constants, 1 and 4. Over here we used intersection. X will be bounded by two functions, y and 8 minus y. All right, there we go. So we have expressed this region R, therefore how do we find the volume? Volume would be double integral of the function, right? The function,
Mm-hmm.
which is 2 plus 1 over y over times dA over region R. So let's go ahead and write it out using our simple principle. So constant must be in the outer. So we should have 1, 4 matching y. So we're going to have dy in the outer. Okay, matching y. Inside, you should have the other variable, which is x. So x is between y and 8 minus y dx. Right?
Mm-hmm.
That's how you set it up. Okay. And over next, let's continue. So over here, we should first of all evaluate this inner integral, right? Inner integral. Okay, so here, inner integral goes from y to 8 minus y. So y to 8 minus y. And the function is 2 plus 1 over y dx. Okay, let's verify this is correct. Yes. All right, is the antiderivative easy here, guys?
Yes.
Because x is the constant, right? There's no x at all. So 2 plus 1 over y will just be the constant, and we should just multiply by an x for its antiderivative. And my x goes from y to 8 minus y. So I can just say, let me keep this 2 plus 1 over y, and let me plug 8 minus y for x, and plug y for x, and subtract those two. So 8 minus y, first of all, and subtract y. I have 2 plus 1 over y times 8 minus 2y. So I can go ahead and distribute, let's do the following, right? So I have 16 plus 8 minus 8 over y minus 4y. And then over here, I have minus 2. Which eventually I get 16 minus 2, which is 14 plus 8 over y minus 4y. Is everything good?
Yes.
Okay, so that finishes our outer layer. Therefore, the volume, which is, sorry, this is the inner layer, right? So inner integral. Therefore, our outer integral will just be from 1 to 4 dy. So 1 to 4 dy, and then copy this whole thing here. So 14 plus 8 over y minus 4y. This is relatively easy for antiderivative. So we have 14y. What's the antiderivative for 8 over y?
Negative 8y divided by y squared.
Remember, over here we have a 1 y, right? Antiderivative will be natural. Yes, log y, right? Natural log y.
Oh, yeah.
For a reciprocal function. And then minus 4y, antiderivative will be 2y squared, right? It's 4 times y squared over 2. And my y goes from 1 to 4. Okay, there we go. You can plug 4n and plug 1n. So plug 4n, I have 14 times 4, and plus 8 times natural log 4, minus 2 times 4 squared, which is 16. And then let me plug 1n, so I have 14 plus 8 times natural log 1, minus 2 times 1 squared, which is 6. Okay, and we know natural log 1 is 0, right? Natural log 1 is 0, so this part just vanishes because it's just 0. So I have 56 plus 8 natural log 4 minus 32, and subtract 14 minus 2, subtract 12. So eventually I have 56 minus 44, which is 12 plus 8 natural log 4 as the final volume of this solid. Any questions, folks?
No.
Nope, great. Okay. So you can see that you'll just need to pay attention for the setup, right? Pay attention for the setup. Other than that, double integral just uses the method we talked about last time for iterative calculation. All right, in the end, let's talk about volume of solid between surfaces, So it's easy to see here. Now, suppose this is a solid. Okay. The solids are actually between two surfaces, okay, between g of xy and f of xy. So for the volume, and it's over this region R, right, over this region R, the volume will just be double integral of the difference of those two functions, v1 minus v2, over dA times dA over R. Does this make sense to you for the integrand?
Yes.
Yeah, basically it's going to be the volume of the solid under Z, right? This total volume, subtract the volume of the solid under G. Okay, so basically it's going to this big volume subtract this small volume, therefore you get the volume in between, right? Volume in between. So it's going to be double integral of the difference of the two functions times dA. Let's finish our very last question here. Let's see, this is a solid. Okay, this is solid. Can you see the solid is between two functions?
Yes.
Yep, one function is going to be this straight plane. right, straight line z equals 5 minus y. The other function is going to be this one. You guys notice? It's going to be z equals 1 plus x squared. Z equals 1 plus, which is the part in blue. Okay, the blue. You can imagine that as a paper folded, right? Folded along the y direction. So it goes up like this. So it actually has something like this arrow going here. So it is this solid between z equals 5 minus y and z equals 1 plus x squared. This solid, if you try to simply try to project it onto the xy plane, it's over this region R. Okay. So the region R has been shown over here. Okay. So let's find the volume. Okay, the volume. So we know the volume should be calculated by using the double integral, right?
Mm-hmm.
Since it's in between two solids, being in between two surfaces, which surface is on top, which surface is to the bottom?
The 5 minus y would be on top.
The straight plane. Yeah, this is on top. This is to the bottom. So we should do the top function minus bottom function, right? 5 minus y, subtract 1 plus x squared, times dA over region R. Okay, now let's look at this region R. Okay, this region R, I'm going to sketch the region R on only xy plane. So y plane. Okay, so the region R looks like it's only constrained by this parabola. Okay, so the parabola is this, which is y equals 4 minus x squared, and constrained by x-axis. Therefore, this is region R, right? This is region R. How would you like to sketch the arrow? Do you draw the arrow from left to right or bottom to top?
Bottom to top.
Bottom to top will be easier. Yes. Okay. So let me go ahead and draw my arrow. Bottom to top. That's for y, right? So the region R is actually y simple. Okay, y simple. The y simple, x has to be bounded by two numbers, and y needs to be bounded by two functions. Okay. Let's first look at the functions, because we have already got the some of the symbols, the functions labeled. So function is easy. What's the lower bound of y? If I draw this arrow, you can see this is the first one, it intersects, right?
Mm-hmm.
This is the second function intersects. The first function is pretty straightforward. Y equals to
0.
0? Yes. Good. What's the second function intersects?
4 minus x squared.
Yep, it's this parabola, which is 4 minus x squared. Good. How about x values?
Negative 2.
X value? Yes, x value is about this x here, left down, and this x here, right?
Mm-hmm.
And actually, those are the two x-intercepts of this parabola. We're going to let 4 minus x squared equals 0. Let this parabola set it equal 0. Correct. So x will be plus minus 2. So here will be 2. Here will be negative 2. So my x will be bounded by negative 2 and positive 2, or the left and right. Good?
Mm-hmm.
All right, so I'm going to ask you guys to complete the volume double integral. Complete its setup. So I can also simplify this. 4 minus 1. Constant to the out, so negative 2 to matching dx. And 0, 4 minus x squared dy margin inside. Is that what you guys got?
Yes.
Okay, great. And then again, we're just going to do the routine calculation, right? And here, 0 to 4 minus x squared, 4 minus y minus x squared dy will just be antiderivative. Okay, so antiderivative will be 4y minus y squared over 2 minus x squared times y, and then evaluate y from 0 to 4 minus x squared. Okay, so you're going to plug everything in, right? I'll just do it here. So 4 times, plug y in, 4 minus x squared minus 4 minus x squared divided by 2 minus x squared times 4 minus x squared. And when you plug 0, you get 0, 0, 0. So minus a big 0. Let me see. Okay, so let me see. So that equals 4 times 4 minus x squared minus 4 minus x squared over 2 minus, oopsie, let me copy this, x squared times 4 minus x squared. All right, very quickly, let me just finish this simplification. You're going to distribute the 4, 16 minus 4x squared minus 1/2, and then find the square. It will be 16 minus 8x squared plus x to the 4th, and then distribute this x squared, 4x squared plus x to the 4th. Eventually, let's do how many x to the 4th there are. We have negative 1/2 x to the 4th and plus 1 x to the 4th. 1/2 x to the 4th. And how many x squared do we have? So let's see, we have negative 4x squared and then add 4, right? Plus 4x squared. So this cancels out and there's additional negative 4, negative 4x squared. For constant, we have 16 minus 8. So it's 8. So that's the inner integral. Therefore, the outer integral will just be from negative 2 to 2 dx, and then 1/2 x to the 4th minus 4x squared plus 8. Okay, so we have 1/2 x to the 6th over 5 minus 4 times x cubed over 3 plus 8x, and you just need to evaluate x from negative 2 to 2. Okay, let me see if we have enough time to finish that. We have 4 minutes. All right, so we have 2 times 5, that's 10, x to the 5th, minus 3/4 x cubed, plus 8x, x goes from negative 2 to 2. When you're evaluating these, you can just plug 2 in and plug negative 2 in, okay? Due to time limitation, I'm not going to finish the calculation here, but you know what to do, right?
Mm-hmm.
And that's going to be your answer. Okay?
Yep.
So in this question, it is the volume of the solid in between those two surfaces, which is in between here. Okay. And this can also be computed by using double integration. All right. Any questions for this lecture so far?
No.
Okay, great. So I think the only thing that, as we mentioned so many times here, only thing that you should pay attention would be how to express the region R that is integrating over. Right? The region R could be X simple, could be Y simple. The way you write it is very important. This is critical in determining if your volume double integration is correctly set up. Okay, I'll assign a few questions for you guys to practice for homework assignments, and don't forget to work on your test 3 take home, right?
Mm-hmm.
All right. If no questions, then our lecture is done today.
Thank you.
No problem. Let me see here. I'm going to see you guys on Wednesday. Okay.